Hello, my name is Christopher Linford, and I want to talk to you about how linked lists could be used in both stacks as well as queues. So when I'm talking about this, I'm going to talk about the times, the big O times for different operations with using linked lists. So let's begin. Let's start with a stack. So a stack follows the last in, first out structure, or LIFO. It means the most recent item is added and the first one's removed. So why would we use a linked list as far as with a stack? Well, what we can do is we can use the head of a linked list. Linked lists have O of 1, or it's more or less like a constant time on there. And what we do is we use the linked lists, allow the O1 insertion and removal at the head. We don't have to shift any of the arrays. No transversals are needed. So when we implement the linked list, we put the head at the top, and this will be optimal because we can, remove and insert at the head. So let's talk about the functions now. Let's talk about push. Push means we add to the stack. And when we do this, I'll create a new node and point it so its next reference is to the current head, and then update the head to the new node. What happens? We create a new node. We point the new node dot next, which is the current head, and then we move the head, or we have the new node. This works because we place the new item on top of the stack instantly without touching the rest of the list. And again, the time complexity is 0 of 1. No loops, no traversal, and just pointer reassignment. Let's talk about pop now. Pop means we remove something from the stack. It has a O of 1 time on here. And what we do is we'll remove the head node by setting the head node to head.next. What happens? We store the head value to the return. We move head to head.next. This works because you remove the top item by skipping over it. And all we have to do is just change one pointer. Let's talk about the next function, which is get top, or we can say peak. And what we do is we get the top value. All we have to do is simply return the data stored in the head node. So we hit the return head.data, and this works because the top element is always at the head, so there's no searching is needed, and that's a 0 of 1 speed or complexity. Next one let's talk about is the isEmpty. It's a 0 of 1 complexity too, and what we do is we want to check to see if the stack is empty. And how do we do that? We just check to see if the head is equal to null. It works because if there's no head node, the stack has no elements. So all stack operations are 0, 1 because we only interact with the head node and we never traverse the list, and make sure that things are pretty fast. Now let's talk about a queue. So what exactly is a queue? A queue is a first in, first out operation. It means the first item added is the first one removed. And what we do is we want to use both the head and the tail. If we only use the head, the enqueue would require a traversal, which is O of n. We don't want that. But if we use both the head and the tail, we add a tail, it's 0, 1. We remove at the head, it's 0, 1, 2. This is the most optimal design. So again, it's a first in, first out. We'd have both a head and a tail pointer in the linked list. And let's start with the functions. So we have enqueue. Enqueue means we add to the enqueue. It's 0 of 1. And all we have to do is add a new node at the tail and update the tail pointer. And what we do is we create a new node. If it's empty, the head is equal to tail, which is equal to the new node. Else tail.next goes to the new node, and then the tail becomes the new node. You always want to add to the back of the line, and the tail pointer lets you do it instantly. 0 of 1 complexity. Next is the dequeue, or we remove the head node and move the head node to head.next. So what happens is we store the head value, we move the head to head.next, and then if the head becomes null, we set the tail as equal to null. This works because when we remove the front of the line, just like the people leaving a queue. Complexity, O of 1. Let's talk about the size. It's a O of 1 complexity 2. To get the size, we want to maintain a counter, and it updates during both the enqueue and dequeue process. So on the enqueue, we add a +1 increment, and on the dequeue, -1 decrement. So with a counter, you need to transverse the list to count nodes. This would be O of n. we don't want to do that. But with the counter, it's O1. Next, we have is empty. Mainly we want to check to see if it's empty. And what we do is we check to see if the head is null. If the head is equal to node null, we know it's empty. If there's no front node, the queue is empty. And then by using a head and a tail pointer, we avoid the transversal, as well as we keep all the operations at Q of 1. So and last, stacks are awesome. With the linked lists, it's optional because the linked list allows constant time insertion and removal at the head. And for the queue, if we use both the head and the tail, it avoids the O1 cost of transverse and doing the in-queue process. Thank you.